In this videotape, we will learn how to solve first-degree equations and inequalities. Now, even with our limited algebraic ability, we are already in a position to solve a simple algebraic equation. For example, 3x plus 7 equals 13 is a typical first-degree algebraic equation in the variable x. Okay, when I say solve an algebraic equation, what I'm trying to do is to find the solution set. That is to find the set of all x values for which this is a true statement. What we have here is something that is not always true and not always false. Rather, it is true for, in this case, a certain x value and not true for others. For example, if x equals 1, we get 3 times 1 plus 7 is 3 plus 7 is 10, so it is not equal to 13. So if x equals 1, this would become a false statement. On the other hand, if x is equal to 2, this would give us 3 times 2 plus 7, 6 plus 7, that equals 13. So for x equals 2, this becomes a true statement, and for x equals 1, it is a false statement. What we're looking to do is to determine the solution set for this equation, the set of all x values for which this is a true statement. Now, our method is going to be to start with this original equation and to reduce it to an equivalent equation whose solution is obvious. This business of trying to transform this into an equivalent equation will be accomplished by using the basic property of equality over here. The basic property of equality says, if A equals B, then A plus C equals B plus C, A minus C equals B minus C, A times C equals B times C, and A divided by C equals B divided by C, assuming that C is not equal to 0. In words, what I am saying is that if we start with an equation, if we add the same quantity to both sides of the equation, we will get an equivalent equation. If we subtract the same quantity from both sides of the equation, we will get an equivalent equation. And if we multiply or divide both sides of the equation by the same non-zero quantity, we will get an equivalent equation. So what we're going to do is start with an original equation, and by following one or more of these basic properties here, we will try to reduce this equation into an equivalent equation whose solution is obvious. Let's start with a very simple equation. For example, x plus 4 equals 7. Okay, we'd like to find the solution set of this equation. What I'm going to do is to subtract 4 from both sides of this equation. This is allowed by property 2 over here. We may subtract the same quantity from both sides of the equation, giving us x plus 4 minus 4, that's just 0, equals 7 minus 4, or 3. So we have now an equivalent equation to the original equation, and in this form it becomes obvious what the solution is, namely x equals 3. And of course we can check this by substituting back into the original equation. 3 plus 4 does in fact equal 7. Let's try another example. X minus 8 equals 3. All right, we can add 8 to both sides of the equation. X minus 8 plus 8 is just x equals 3 plus 8, or 11. Once again, we have reduced this to an equivalent equation whose solution is obvious, namely x equals 11. Our goal is to eventually get it down to a form where we have x alone on one side of the equation equals some number, and that would be the solution of the equation. Let's try another example. (4x equals 20). All right, in this case, what I'm going to do is to try to get x alone on one side of the equation. Now, in each case, I sort of had to undo something to get x alone. I had x plus 4. I had to subtract 4 from both sides to get x alone. X minus 8, I had to add 8 to both sides. We have here 4 times x. To undo this, I'm going to divide both sides of this equation by 4. 4x divided by 4, the 4's will cancel. We will have just x equals 20 divided by 4 is 5. So x equals 5. Now, a word of caution. Okay, sometimes people get sloppy and they say, well, I'm going to subtract 4 from both sides. They think, well, you have the 4 here. If they'll subtract 4, and they say x equals 16. Clearly, that's not the answer. 4 times 16 is not equal to 20. 4 times 5 is equal to 20. Be careful how you undo what you've started with. We undo addition by subtraction. We undo subtraction by addition. And we undo multiplication by division, not by subtraction. Okay? How about 5x equals 0? To solve this equation, once again, x is joined to the 5 by multiplication. We will divide both sides by 5. 5x over 5 gives us just x. 0 over 5 is 0. Checking this, 5 times 0 is equal to 0. Remember that 0 divided by 5, or 0 divided by any non-zero number, is 0. 5 divided by 0, however, that would be undefined. Okay, it's division by 0 that's not allowed. We can have a 0 in the numerator. 0 divided by 5, the answer is 0. Okay, let's go back to the equation that we started the tape with. (3x plus 7 equals 13). Now I want to solve for x. Okay, this is a little more complicated. In all the equations we've solved so far, we only really had to use one of these 4 properties. Here we have to do more than one thing. We'd like to get x alone on one side of the equation. So the first thing I'm going to do is to subtract 7 from both sides. This will give me 3x plus 7 minus 7, or just 3x on the left, equals 13 minus 7, or 6. And now to get x alone, I will have to divide both sides of the equation by 3. 3x divided by 3 is just x. 6 divided by 3 is 2. And of course, we can check this in the original equation. 3 times 2, 6 plus 7 does in fact equal 13. Okay, let's try some more examples. (7 minus x equals 12). I'd like to get x alone on one side of the equation. I'm going to subtract 7 from both sides, giving us 7 minus 7, that drops out, and minus x equals 12 minus 7, which is 5. Okay, now I'd like to get x alone on one side of the equation. Remember that minus x is really minus 1 times x. So just like before, when I wanted to solve for x, I divided by the coefficient of x. Same thing over here. I will divide both sides by minus 1. Minus 1 times x over minus 1. The minus 1's cancel, and we get x. 5 divided by minus 1 is minus 5. So I get x equals minus 5 as my answer, and I can check in the original equation. 7 minus x equals 12. I want to check 7 minus, now x is minus 5, should equal 12. 7 minus a minus 5 is 7 plus 5, should equal 12, and of course 12 equals 12. It checks out. All right, for next example, let's try this. 5 minus 3x equals 14. Our goal is to get x alone on one side of the equation. Okay, I'm going to subtract 5 from both sides, and I'll get minus 3x, because the 5 and the minus 5 cancel each other out. 14 minus 5 is 9. I will now divide both sides of the equation by minus 3. Minus 3x over minus 3 gives us x. 9 plus 9 divided by minus 3, the result is minus 3. And to check, we're checking that 5 minus 3x equals 14. 5 minus 3 times minus 3 should be equal to 14. Well, this is 5. Minus 3 times minus 3 is plus 9. The multiplication, of course, is done first because of order of operations. And 14 does equal 14, so it checks. For our next example, let's try this. 2x minus 5 equals 6x minus 9. Now, this is a little different from the other problems because the variable x occurs on both sides of the equation, and so do the constants, in fact. What we have to do is get x alone on one side of the equation, and it can be on either side, whichever you would prefer. So, for example, you might decide to get the variable alone on the right side and the constants on the left side. To do that, I would subtract 2x from both sides of the equation. 2x minus 2x gives you 0. Minus 5 equals 6x minus 2x is 4x, and minus 9. I want to get x alone on the right, so I will add 9 to both sides of the equation. Minus 5 plus 9 is 4, equals now 4x. Minus 9 plus 9 is 0. And to solve for x, we have to divide both sides of the equation by 4, giving us 1 equals x, which is just as good as x equals 1. This means the same thing as x equals 1. And we can check in the original equation. 2 times 1, 2 minus 5 gives us minus 3. 6 minus 9 is also minus 3, so it does check out. Let's try a slightly more complicated equation. 7 minus, in parentheses, 5 minus 2x equals 3 times, in parentheses, x plus 2 minus 8. All right, now here what we have to do before we get to a point like we were over here, where we have, say, variables and constants on both sides. First, we have to simplify the left side as far as we can and the right side as far as we can. We're going to remove the parentheses and combine like terms. Okay, so the first thing we're going to do is to remove the parentheses. To do that, we have to realize that minus here means a minus 1 is to be distributed through the parentheses. 7 minus 1 times 5 is minus 5. Minus 1 times minus 2x is plus 2x equals, here we'll have to distribute the 3 through parentheses. 3 times x plus 3 times 2, which is 6, now minus 8. Having removed the parentheses, the next order of business is to combine the like terms. 7 minus 5, that's constant. These are constants. They can be combined. That's 2 plus 2x equals 3x plus 6 minus 8. That's minus 2. And this problem now looks like the previous one, where you have variables and constants on both sides. And all you have to decide is which side you'd like to put the variables on. You do not have to always get x on the left side or always get x on the right side, whichever you feel more comfortable with. Let's say we get x alone on the right side. We can subtract 2x from both sides of the equation. That gives us 2. Plus 2x minus 2x is 0. 3x minus 2 minus 2x. 3x minus 2x gives us 3 minus 2, or 1x, minus 2. And then add 2 to both sides of the equation to get the constants on the left side. We get 4 equals x minus 2 plus 2, or just x. So the solution becomes x equals 4. To check this, let's go back to the original equation here and substitute in x equals 4. 7 minus 5 minus 2x, or minus 2 times 4, should be equal to 3 times, in parentheses, 4 plus 2 minus 8. Okay, 7 minus. Now, order of operations dictates that this multiplication occurs before the subtraction, so we have 5 minus 8. 2 times 4 is 8. Should be equal to 3 times 6 minus 8. 7 minus, now 5 minus 8 is a minus 3, should be equal to 18 minus 8. 7 minus a minus 3 is 7 plus a plus 3, or 10 equals 18 minus 8, which is 10, so it does check out. As our next example, let's try this. 6 minus 3 times 4 minus x equals 3 times x minus 2. All right, as before, let us remove the parentheses first. 6, now minus 3 times 4 is minus 12. Minus 3 times minus x is plus 3x equals 3 times, now distribute the 3 through these parentheses here, 3 times x, and 3 times minus 2 is minus 6. So we get that 6 minus 12, combining, is minus 6 plus 3x equals 3x minus 6. Adding 6 to both sides of the equation, minus 6 plus 6, they drop out. You get 3x here equals 3x here, and the minus 6 and plus 6 drop out. If we then subtract 3x from both sides of the equation, an interesting thing occurs. We get 0 equals 0. Okay, now this is a little different from the other equations that we were solving. We see that the variable has completely dropped out. And what we have come to is an identity. 0 equals 0. In fact, it was apparent at this line already that what we had were the left and the right side identically equal to each other. 3x minus 6 equal to 3x minus 6. When you try to solve an equation, what happens is the variable drops out, and you wind up with something which is always true. In this case, an identity like that. This means that the original equation was something that was true for all x values. Okay, actually, the equations that we've been solving so far, equations like the one that we had over here, these are really conditional equations. That is, they are true for certain x values and not true for other x values. What we have here is an identity. This type of equation that we have over here is an identity. It is true for all x values. And your tip-off is that when you try to solve for x, you wind up with an identity. The variable has dropped out, and you just get, say, 0 equals 0. So we have here an identity. The equation is true for all x values. Let's try another example. X plus 5 minus, in parentheses, 2 minus x equals 8 plus 2 times parentheses x minus 2. Here we get, removing the parentheses, x plus 5 Here we have to distribute a minus 1. Minus 1 times 2 is minus 2. Minus 1 times minus x is plus x equals 8 plus, distributing the 2, 2x now minus 4. Don't forget the 2 multiplies the x and the minus 2. Combining the like terms on the left side, we have x and x, that's a 2x. 5 minus 2, that's a plus 3, equals, and on the right side we have 2x. 8 minus 4 is plus 4. Subtracting 2x from both sides of the equation, we get 3 equals 4. Okay, now obviously 3 is not equal to 4. What does this contradiction mean? It means that the original, this is equivalent to the original equation. Since 3 is never equal to 4, that would mean the original equation can never be true. In other words, there is no x value for which the original equation is true. So once again, we have seen that we get down to a point where the variable drops out. But unlike the last case where we got down to something which was always true, namely 0 equals 0, here we get down to something which is always false, 3 equals 4. This tells us the equation is not true for any x value. And what we have here are the 3 possibilities that might occur. We have over here an example of a conditional equation. We go through, we solve it, we got x equals 4 as a unique solution to this first degree equation. We can go back and check it. This is the only solution to this equation. In the other 2 examples, the variable dropped out when we tried to solve. In one case, it resulted in an identity. This implies that the original equation is true for all x values. In the last example that we worked out, we got down, the variable dropped out, and we got down to a contradiction, which means that the original equation is not true for any x value. Okay, now we can use what we know about solving algebraic equations to handle some very simple verbal problems. Okay, now you will be working a lot on verbal problems, on word problems in your algebra classes. They're not something to be scared of. What you really have to do is read the statement of the problem very carefully and try to see if you can get an equation to come out of the words of the problem, and then you go and solve this equation. Let's try a very simple example. The sum of 2 numbers is 30. If 4 times the smaller number is 12 more than 2 times the larger, find the numbers. Okay, now, we're dealing with 2 numbers that sum to 30. Let's let x equal the smaller number, and then 30 minus x could represent the other number, let's say the larger number. X and 30 minus x are 2 numbers that add up to 30. For example, if x were 5, 30 minus 5, 25 would be the other number. 5 and 25 would add up to 30. If x were equal to 10, 30 minus 10, 20 would be the other number. Okay, now we're told that there has to be a certain condition satisfied between these 2 numbers. 4 times the smaller number is or equals 12 more than 2 times the larger. 4 times the smaller number. 4 times the smaller number. 4 times x represents 4 times the smaller number is, translates to equals, 12 more than 2 times the larger number. Four times the smaller number, x represents the smaller number, is equals 12 more than 2 times the larger number. So what we were able to do is to translate this word problem into an algebraic equation that we are now capable of solving. Let's try to solve it. Let me rewrite it over here. 4x is 2 times 30 minus x plus 12. Removing parentheses. 4x is 2 times 30, that's 60. 2 times minus x is minus 2x plus 12. 4x, let's combine. 60 plus 12, that's 72 minus 2x. Let's get everything with x on one side and all the constants on the other. So we add 2x to both sides, giving us that 6x equals 72. And to solve for x, we'll divide both sides by 6. X equals 72 divided by 6, or 12. Okay, so x is 12. That's the smaller number. 30 minus x would be 30 minus 12, 18. This is the larger number. So the two numbers are 12 and 18. And let's check to see if we have solved the problem. Now, to check a word problem, you don't go back to the original equation because, after all, you might have made a mistake in writing the original equation. You go back to the words of the problem. We're looking for two numbers that sum to 30. Well, 12 plus 18, they do sum to 30. So that part checks out. Now we want 4 times the smaller number to be 12 more than 2 times the larger. 4 times the smaller number, 4 times 12, should be 12 more than 2 times the larger number. 4 times the smaller number should be 12 more than 2 times the larger. Let's see if that checks. 4 times 12, that's 48, should be equal to 36 plus 12, and 48 does equal 48. So that checks out. So we do have here two numbers that sum to 30, and for which it is true that 4 times the smaller number is 12 more than 2 times the larger. Okay, let's try another simple example. Find 3 consecutive integers whose sum is 36. Okay, let's let x equal the first of these integers. Then the next one would be x plus 1. And then one after that would be x plus 2. These are 3 consecutive integers. For example, if x were 5, 5 plus 1 would be 6, 5 plus 2 would be 7. You'd have 5, 6, and 7. X, x plus 1, x plus 2 represent 3 consecutive integers. Now, aside from being consecutive integers, we want the sum to be 36. We really don't have to have the parentheses here. I'm just pointing out that we're adding up the 3 consecutive integers and getting 36. X plus x plus x, that's 3x, plus 1 plus 2 plus 3 equals 36. subtracting 3 from both sides of the equation. 3x equals 33. And to solve for x, dividing both sides by 3, x comes out to be equal to 11. Well, if x is equal to 11, that would mean the first integer is 11. The second is 11 plus 1, or 12. The third is 11 plus 2, or 13. Here we have 3 consecutive integers, 11, 12, and 13. And what do they sum up to? 1 plus 2 plus 3, 6. 1 plus 1 plus 1, 3. 3 consecutive integers, and they sum to 36. So we have solved the problem. OK, now let's work with solving first-degree inequalities. To remind you about the inequality symbols, I can write 2 is less than 3. This symbol means is less than. I can write 4 is less than or equal to 5. This means is less than or equal. And I can write also 4 is less than or equal to 4. These are all true statements. I can also write 5 is greater than 1. I can write 6 is greater than or equal to 3. And I can write 6 is greater than or equal to 6. Here the equal holds, and here the greater than holds. This means greater than or equal, that one of the two should hold. OK, now a first-degree inequality looks something like this. 4x minus 3 is less than 13, and we are trying to solve this. Find the set of all x values for which this is a true statement. Now, it's very simple to work with first-degree inequalities. Basically, you go about solving a first-degree inequality the same way you go about solving a first-degree equation, except when it comes to multiplication or division by a negative number. When you multiply or divide both sides by a negative number, you have to reverse the direction of the inequality. In other words, you are allowed to add the same quantity to both sides of the inequality, and you get an equivalent inequality. You can subtract the same quantity from both sides, and you get an equivalent inequality. You can multiply or divide both sides of the inequality by the same non-zero quantity, and you get an equivalent inequality. If, however, you multiply or divide by a negative number, negative quantity, you have to reverse the direction of the inequality. OK, let's see what we can do. Once again, our goal will be to isolate x to get it alone on one side of the inequality. So over here, I can add 3 to both sides. And I would get 4x minus 3 plus 3, or 4x is less than 13 plus 3, 16. And then I can divide by 4. Now, 4 is a positive number, so I don't have to do anything with the inequality. 4x over 4, that's x, less than 16 over 4, that's 4. And the solution for this inequality is all x values that are less than 4. For example, if x were equal to 3, you would expect that this would be a true statement because 3 is less than 4. If x were equal to 3, you'd have 4 times 3, 12 minus 3, 9 is less than 13. It is true. On the other hand, if you pick an x value that's bigger than 4, let's say 6, you would expect it not to work. 4 times 6, 24 minus 3, 21 is not less than 13. So the set of x values for which this is a true statement is all those x values less than 4. Can indicate this on the number line. 1, 2, 3, 4. This would be minus 4. We want all x values that are less than 4. We can do this in the following manner. This represents all x values. These are the possible solutions to this is a set of all solutions to this inequality, all x values that are less than 4. This open circle means 4 is not included. Let's try another example. 5 minus 2x is less than or equal to 9. OK, we want to solve for x. We'd like to get x alone on one side. We will subtract 5 from both sides, giving us minus 2x less than or equal to 4. Okay, now I want to divide both sides by minus 2. You can divide both sides of the inequality by minus 2, but when you divide by a negative number, you must reverse the direction of the inequality. So instead of less than or equal, it becomes greater than or equal. Now, minus 2x over minus 2, you get just x, greater than or equal 4 plus 4 over minus 2, that's minus 2. So the solution set would be all x values that are greater than or equal to minus 2. And this could be indicated on the number line as follows. All x values greater than or equal to minus 2. This would be greater than minus 2, and if you fill in the circle, that means greater than or equal to minus 2. Going back over here, x less than 4, strictly less than 4, you had an open circle here, and all values less than 4. Here, greater than minus 2, but the closed circle, the filled-in circle here tells me minus 2 as well. Greater than or equal to minus 2. Okay, let's try another one. 3 times x minus 1 minus 4x is greater than 2. 3x minus 3, distributing the 3 through the parentheses, minus 4x is greater than 2. 3x minus 4x, that's minus x minus 3 is greater than 2. You can add 3 to both sides, giving us minus x is greater than 5. And remember, this is really minus 1 times x. So I'd like to divide both sides by minus 1. But if I'm going to divide both sides by minus 1, I'm going to have to reverse the direction from greater than to less than, giving me an answer of x less than minus 5. And we can sketch the answer here. Sketch the graph of the solution set. All x values less than minus 5. For our last example, let's try the following. Minus 7 less than or equal to 6x minus 1 less than 11. Here we have a continued or a double inequality. This means minus 7 is less than or equal to 6x minus 1, and 6x minus 1 is less than 11. In other words, 6x minus 1 is between minus 7 and 11, possibly equal to the minus 7. Okay, what we can do is, in this case of the continued or double inequality, we want to get x alone in the middle. We can add 1 to all parts of the inequality, giving us minus 6 is less than or equal to 6x less than 12. And then to get x alone, we divide all parts by 6, which is a positive number, so we can keep the same directions. Minus 6 over 6 is minus 1, less than or equal to 6 over 6, that's 1x, less than 12 over 6 is 2. So the solution set would be all x values between minus 1 and 2, possibly equal to minus 1, but not equal to 2. And we can sketch the graph. Whereas between minus 1 and 2, not equal to 2, but possibly equal to minus 1. Everything from minus 1, including minus 1, up to, but not including 2. I do want to mention that when you're solving inequalities, it is possible that you will get down to a point where the variable drops out, and the resulting inequality is either always true or always false. This is similar to the work that we did in contradictions and identities and solving equations. If the variable drops out and what you get is something which is always true, then the original inequality is true for all values of x. If what you get is something which is always false, then the original inequality is true for no value of x. And that brings us to the end of this tape.